All right, so here we are in the machine learning class, and we're down to artificial neural networks, which, this is wonderful. I actually did brain research and brain computer modeling many years ago, and I'm, as always, extremely pleased to see how it turned into something good years after I wasn't in the game anymore. Wasn't much good when I was doing it. So this is inspired by our brains. It is not a very close biological model, but it is inspired by the way our brains work, and that shows it must be possible. Our brains have 10 to the 11 neurons, which is a lot, but they're very slow computers. Each neuron takes several milliseconds to do one calculation. And we can respond to things very fast, like 50 milliseconds. Like if there's a rock coming at your head, it jerks out of the way. So just a few cycles is all you have in a real human biological brain. And so if we could just make computers that work that way, it would give them a lot of special properties. So artificial neural networks are at the core of deep learning, and they're used by all the powerful things we really have now, like Siri and YouTube, recommendation engines, and so on. So we're going to talk about how biological neurons work in a very simple way, and artificial neurons, and then the perceptron. The perceptron existed when I was doing this a decade or two ago, but it was just a sort of curiosity, then it couldn't accomplish anything. It was like a sort of a mathematical example of the simplest neural net. But the multi-layer perceptron, and especially the new discovery of backpropagation, had made it possible to actually efficiently tune a perceptron, and this is what we're actually using these things now. We'll talk about them. So, biological neurons, and the history, this thing's been around since 1943. I mean, AI has been around forever. It's just been so weak that you couldn't get anything much done. And so there was several times there's been people propose some artificial intelligence system, and it gets popular briefly, and then people discover it isn't really any good. And there's a long winter for it. And then in the 1990s, they developed more machine learning systems. And again, it died out because they didn't go far enough. And now there's a new wave of interest as there's a jump forward in the technology. And now I think largely because of ChatGPT, people are amazed and convinced that it's really going to work this time. All right, so there's a huge amount of data now available, which was necessary before. And artificial neural networks are very good at large and complex problems. The training algorithms have improved greatly, which is what we're going to talk about largely here. And it turns out that there are theoretical problems, like you might settle into a local minimum and you can't find the global minimum, and it turned out not to be a big problem. So right now we're in a virtuous cycle of funding and progress where people are making products that get a lot of attention, that attract more funding, and so on. Very much like the cryptocurrency boom a few years ago, with the difference that cryptocurrency didn't actually seem to do anything. Didn't seem like you need it, didn't seem like a normal person benefited in any way from it, whereas artificial intelligence does power things that we can use every day and appreciate. So it seems like it's a boom with real substance and probably some real staying power. All right. So biological neurons look like this. You have a cell body, and then you have these dendrites coming out, which are these short spikes. These dendrites connect to nearby neurons, so they get signals from a certain bunch of neurons. They add up the data it's getting from all of them, and it pumps the output down an axon. It builds up a concentration of a chemical until it fires and sends one electrical pulse that goes down a long axon to the output somewhere else. And so that's the idea. And the action actually happens at these synapses, where the one cell catches another, and then it transmits neurotransmitters of various kinds here. But from a viewpoint of our machine learning, it's enough to think they just combine the signal from many other neurons and calculate an output which they send to another neuron which can be far away, for example, in another layer. All right, so those are called action potentials that travel along the axons, and then they release neurotransmitters at the synapses. And when a cell gets enough neurotransmitter, it fires and sends a signal out its axon. That's how these things work. And here's some human cortex. This is what it looks like. You have all these long axons connecting them and somewhat layers of neurons here. So that's the thing. So the computation is done by all these neurons working together like a complete brain. And we really don't understand too much of exactly how it works. But now we managed to get pretty far with these digital, or I should say electronic analogs. Although in fact the ones we're using are digital. So, do logical computations with neurons. The simplest neuron would just be on and off. So if it gets enough signal, it turns on, otherwise it's off. So you can have, to perform an equal operation, you just take the outputs of this one and feed it into that one, and if this is firing, those ones will fire. Here you can do A or B, where they both go in here. If either one of them is positive, the output will be positive. Here you're doing A, not B, I think. I'm like, yeah, or. This is or. Okay, this is A and B. Okay, where these two have to add up to a big number to get there. Here's A or B, so you need two signals coming in positive for this one to be positive, and here you have two signals out of each of these, so if either one of them is on, then this will be on. And here's not, and this is going to be and not be. You can do this. So you just invert this one. So this one suppresses firing. So if this one is firing alone, and this one is not firing at all, you get a positive. But if this one is firing and this one is firing, this one cancels out one of them and you don't have enough to fire. So you can do certain combinations of them with a single neuron. And the perceptron works like this. And it's been around for an awful long time. And let me get rid of this noise. All right. All right. So the neurons are threshold logic units, or linear threshold units they call them. And these are things to take a linear function of the inputs. They have a weight on the input from somewhere else, another weight, another function, and then they have an offset. And it applies a step function to the results. If the total of all this is above 0, then the output is 1. If it's below 0, then the output is 0, or you can adjust where that threshold is. That's the simplest way. So one threshold logic unit can perform a binary classification. You feed in these inputs. It does a linear function to combine the signal coming in those inputs, and then it goes through a step function. If the total of all that is high enough, you get a 1, otherwise you get a 0. And that's it. All right, and that's the game. So you train it just by adjusting these weights and the bias, and that's called a perceptron. Is a layer of these things. Every TLU is connected to every input, so it's fully connected. And so here's the input layer, and the threshold units are the output layer, and that's it. This is a single layer of neurons. And so it can classify instances into 3 classes. You can put in your inputs, and if you've got 3 outputs, it has a signal coming out of these 3, and you can say you can train it so one of these that puts out the strongest signal is the categorization of these. So it can sort inputs into 3 classes. All right, so to train it, this is the simple rule. Whenever a neuron triggers another neuron, often the connection between them gets stronger. You can also feed back the error in, this is unsupervised learning, where it just sort of develops a habit of doing whatever it does most often. This is supervised learning, where you feed back some kind of error, and it knows whether it's getting things right or wrong, and it reinforces the connections that get more answers right. So if you want to train it, you can do stochastic gradient descent, where the next step you take the current weight and you add a step size, this is a learning rate, times the output. So the y is the output of the neurons. So that connects to I and j, you connect the difference between the neurons, and you have the target output, yj. So you compare the current prediction with the correct value, and you change the weight in the direction that will make it closer to the correct value. That's all this means. This is supervised learning, where you have a table of correct values to compare it to. All right. So the problem is it's linear in all inputs. If you have a bigger signal from here, it's a bigger signal there. And that means you can't do XOR. A very simple operation where if x1 is 0 and x2 is 0, you want 0. And if they're both 1, you want 0. But if they're only one of them is 1, you want 1. And since it's linear, when they're both feeding in a 1, you'll get a bigger answer than here. And so the one single perceptron cannot do this. So with 2 perceptron layers, you can do XOR. And so you feed this in with weights 1 here to both of these. Then you have these weights here and so on. And I worked through it. I'm not sure it's worth going through in much detail. Well, let's just try one of these. So here I feed in 2 zeros. And now I multiply them here. So that's going to have the inputs are all going to be 0 here. So this one is going to be 0 plus 0 minus 3/2. And this one is going to be 0 plus 0 minus 1/2. So this is going to be minus 1.5, and this is going to be minus 1/2. Now, I multiply this one by minus 1 and put it here. So that's going to turn it into, because it's minus 1/2, the output is going to be 0. And because this is minus 1/2, the output is going to be 0. Because the negative values, this is step function, will kill everything that's below 0. So now I'm going to have 0 times minus 1 and 0 times minus 1 here. So the output's going to be minus 1/2, so I get 0. So if I feed in 2 zeros, I get 0. Now, if I feed in 2 1s, I will get, all these inputs will be 1, so I have 1 plus 1 minus 3/2. That's 1/2, so the output will be 1. Here I get 1 plus 1 minus 1/2, that's 1.5, so the output will be 1. So now I'm feeding 2 signals of 1 in here. This one gets multiplied by minus 1, this one by 1, so they cancel out, and this minus 1/2 means I get an output of 0. So when they're both 1, I get 0. And here, if I have 0 on the left and 1 on the right, then the 0 goes here and here, and the 1 goes here and here. So this one's going to be 1 minus 3/2, which is minus 1/2. This one's going to be 1 minus 1/2, which is 1/2. So the outputs of this layer are going to be 0 and 1. And this one will feed in there as 1, and the output of this layer will be 1. So when the two are different, you get 1. So that's, you can work through it and see this way that 2 layers of perceptron are enough to do that nonlinear XOR operation. And that is why we have multi-layer neural nets. We discovered, as your biological brain discovered, that having several layers makes it possible to do much more interesting calculations than just one layer. And in a sense, I would like to say this ties into the psychology thing. There was a guy called B.F. Skinner who proposed that all we have is simple reflexes, like you poke a frog's leg and it jerks. And he said that's all human behavior is. And all the cognitive psychologists of the world said, no, humans are more complicated than that. And this is the thing. I think his idea was that we're like a perceptron, and that's ridiculous. We are a multi-layer perceptron, where we have more complicated responses to inputs. Anyway, let's try a Kahoot. I've got them here. And this is 10A. All right. Such linear is some kind of concession to super large scale of variable quantity. I'm not sure I understand what you're saying there. However, linear operations, you can't scale up, of course. That is an issue. And why am I getting no sound? Oh, there it is. All right. I'll wait for the end of the song, I suppose. We may have only 3 competitors. Such is life. All right. All right, so what part of a neuron branches out to get signals from nearby neurons? That's the dendrites. The axon is the one that goes far away. The dendrites are the nearby ones. There's a bunch of dendrites feeding in and only one axon coming out. Right. One of these can perform a binary classification. A single threshold logic unit. A single neuron can do that. Oh, we have 4 people. Somebody else must have joined. All right, good. All right. And it takes 2 of these to compute XOR. It takes 2 layers of perceptron to do it. All right, good. All right. Okay. So the multi-layer perceptron. This is the big punchline of this chapter, I think, backpropagation. So this is a feed-forward neural network. Input comes in here. It goes to the hidden layer. That goes to the output layer. All the signal goes one way. Nothing ever comes back the other way. And there can be a deep stack of these layers. It can go through many of these, and that's called a deep neural network. But it's still a feed-forward neural network. The signal only goes in one direction. But in 1970, they developed this technique called reverse mode automatic differentiation. And what this does, see, when I did this, I wondered, you have all these parameters. You have a slope and intercept where every one of these arrows touches. So there's a lot of parameters. How do you optimize that many parameters? If you have like 10 or 100 choices of each parameter, very soon you've got some number like 100 to the 100 calculations, more than you can ever do. So how do you optimize it? This is the special trick. You send a signal backwards through the network, and you can calculate how much each of these weights is contributing to the output. And so you can calculate the gradient with respect to each of these weights. You can determine which direction will change the output up or down, and therefore which direction will get closer to the desired value. So you can figure out which direction is improving the model without having to do some monstrously complicated calculation. It's really nothing more than a bunch of derivatives. So this turned out to be the essential thing. So reverse mode autodiff and gradient descent is called backpropagation. And that is the essential tool necessary for gradient descent. You have to be able to figure out which direction is pointing down, and now you have an efficient way to do that. So here's what you do. You initialize all the weights randomly. Now you use a mini batch to make the calculation practical. You run that batch through the network to the end, measure the error, and now you analytically calculate how much each weight and bias contributed to the error, and now you can figure out what direction will lower the error and move in that direction. So now you can figure out, without it taking a ridiculous amount of calculation, you can figure out how to make a descent. Now, the problem is, if you've been using a step function, then there is no gradient. There's just, things don't change at all until you hit 0, then they change abruptly. Now you can't do a gradient descent because there is no gradient. There's just a cliff to fall off. So you have to have a smooth activation function, not this heaviside step function we've been talking about. So you have to choose one of these smoother functions, and there's a variety of them. One of them is the rectified linear function here in purple, where you let this part be flat, but then you give it an upward slope here and just have it keep going. Then there's these ones that are smooth, like hyperbolic tangent and sigmoid, which is the sum of a Gaussian that just gradually goes from here to there. So these, all right. And so this is the default, is the rectified linear because it's faster to calculate, but you'll see the others are generally better. Anyway, because you do need to have something with a slope, or there won't be any slope to go down. How many rounds does backpropagation consist of? One pass, no rounds. So you calculate it forwards, and then you have, you use the chain rule to analytically calculate it going back. So you compute how much it contributed to the error. So you don't go through any cycles or anything. Once you've got one measurement, you can calculate how much each of the weights contributed to that measurement just analytically. And from that, you can calculate analytically which direction will lower the error. That's the idea. Basically, what you assume is that it's all locally linear near that point. This is a very common trick in physics. You have some function that's complicated, but you make a small perturbation and you assume that it's linear within the range of that small perturbation. And that's why this works. You can make a small step and it will have the expected result as long as your step size is relatively small. And since it's not really linear, you'll have to keep changing the step direction as you go down. You have to keep recalculating it. All right. So that's the game here. So now if you talk about regression, if you want to predict a value, you have one output neuron, you feed in your inputs, you go through your hidden layers, and then your output is one output neuron. We've done that. If you want to predict a two-dimensional value, that's two outputs, one for x and one for y. So that would be the x and y coordinates of something. Right. Yeah, locally linear but globally curved. That's exactly right. All right. So you have to have your output neuron has to have an activation function. Now, if you just are happy to have a varying value and you don't really care what range the value goes over, you can just leave it unchanged and then say a higher signal is a higher probability of this or something. If you want to guarantee a positive value, you could use a rectified linear function, or you could use soft plus. Soft plus is one here that will make sure that's another way to do it. You can also use sigmoid or tan H. These are various ways to scale the output. Now, you have to have some way of measuring the error. When you're done, you predict something, and you have knowledge of what the right answer is, so you have to somehow measure the difference between the predicted answer and the right answer. Usually you predict the mean squared error. If you have a lot of outliers, you might use absolute error to avoid counting large errors much more than small ones, or you can use this thing called Huber loss, which combines both of them. So here's the typical regression architecture. You have a hyperparameter, and your typical values, the number of hidden layers, 1 to 5, for example, some number of neurons in a layer, like 10 to 100, 1 per prediction output dimension of output neurons, and you typically use ReLU for the hidden layers, this thing that is flat on the negative side but has linear growth beyond that. For your output activation, you can have none if you want a wide range of output, or you can put one of these things here if you want to just have bounded outputs. And to measure your loss, you use mean squared error or Huber, which is a combination of mean squared error and linear absolute value error. These are also called the L2 error and the L1 error. One is the second power of the error and the other is the first power of the error. All right. And if you want to have a classification model, if our binary classification, you have one output layer, you feed in your inputs, go through your hidden layer, you have one output, which is the probability of the output being 1 or true, and a sigmoid activation function. So that's the probability of the positive class. And we've done this. For multi-label, you have multiple outputs. And in this case, we're considering where both of them might be true. So you're going to label emails spam and urgent, and both of those could be true, or both of those could be false. So each of these will just be a sigmoid function individually, going from 0 to 1 in the probability. If you only allow one class per instance, like, for example, that case where we were sorting images of clothing into 10 categories like shirt and shoe and such, but only one of them can be true, then you don't want to. Then you use this thing called the softmax function, which scales them all so the total probability will always be 1. And that's what the softmax function looks like. But that's what it does. It just scales them so that they add up to a total of 100%. And so here's the classification architecture. Yeah, again, 1 to 5 layers. And your output neurons are 1 for binary, or 1 for label for multi-label, and for multi-class you'd be 1 per class. And I think multi-label is where many labels can be true, and multi-class is where only one of several classes can be accepted. So you use softmax here, so total percentage will be 1. You use sigmoid here, so each single one of them is scaled from 0 to 1, and it's the probability of it being the 1 case. And then you have a loss function, and you need X entropy in all these cases, cross entropy. We've talked about this. If you have an output like classifying something in 10 categories, and you know what the right category is, there's not a distance to define how wrong you are. You have to take the probability that you got it right and the probability you got it wrong any of 9 ways and combine those with a negative logarithm function, the way you typically calculate entropy. It's just a measure of how right you were. So it's something that will be maximized when you're getting it 100% right, and it will get smaller when you get more and more of it wrong. Just a way to measure. And here it is, cross entropy. There's the sum of it. It's the sum of the target probability that it belongs to class K times the log of, I think P is the right answer. No, Y is the right answer, and P is the prediction answer, I think. Anyway, I'm not going to worry about the details, but that's very much like Shannon entropy. It's just a way to come up with a single value that measures how correct you were in your prediction. All right, let's try another Kahoot. 10B is here. All right. All right. Well, from the avatars, I think Woot has the advantage. All right, let's go. All right, so what method was developed in 1970 to make gradient descent easier? Yeah, the reverse mode autodiff. So you can figure out which direction is going to lower the loss, and therefore which direction to make a step in. All right, what measure of loss works for multi-label classification? You need that cross entropy thing because you're having to calculate a whole bunch, to boil a whole bunch of probabilities down to one number. You have like 10 categories and a probability being each of those 10 categories. So cross entropy is the mathematical measure of how close you were to correctly predicting it all. All right, what activation function makes sure that the total of all the outputs is 1? All right, it's softmax. Okay, good. All right. All right. All right, I've got the winners. Let's go back to here. Okay, so to implement this stuff with the Keras Python library, we've done this before. You do the 28 by 28 grayscale images of clothing, And you can load the data set here where it's going to split it into training set and a test set. And you're going to set aside a validation set and divide by 255. So here we define X validation. So this is going to be the training is going to be the last 5,000. That's what this will do, colon minus 5,000. And the validation set is going to be the first 5,000, I think. I don't quite understand what it means when you put a minus sign here in Python. I'd have to ask Bard or go to a Python library to find out. But anyway, you set aside 5,000 of them for training and another 5,000 of them for validation. And you don't want to have pixels that vary from 0 to 255. These machine learning models would like you to have things that go from 0 to 1 or minus 1 to 1. So you divide it by 255 to normalize them. Okay, so now we make a sequential model, which is going to be the usual feed-forward model where each layer just feeds to the next layer and the next layer, and you have one pass. So the first layer is flatten, which is going to take the input shape of 28 by 28 and just spread it out into like 784 individual neurons because it doesn't like two-dimensional input. Then we're going to have 300 layers, 300 neurons in a hidden layer, densely connected, so every one of these input pixels will go to every one of these, and then another layer of 100 neurons, and these are going to use the simple default activation function, the one that is 0 if for small signals, and then has a straight line growth beyond there. And then at the end, we're going to have softmax at the end, which will make the total probability add up to 1 for the 10 layers. So it'll divide the thing into 10 categories with a total percentage of 1. That's what you've got here. This will be done before. So you have the image being separated into a line of pixels, going into a hidden layer and another hidden layer, and then set up into outputs. So if you do a summary, the flattening has no parameters. That's just taking the 28 by 28 pixels and spreading them out, so it's not doing any adjustment at all. This dense layer is going to have 784 times 300 parameters. A parameter for each of these to come in, and then I think an offset. So, it's going to take you way up to this number, 235,000. Then this dense layer is going to have 300 inputs, each going to each of these 100. And then a bias at each cell. So it's going to be 300 times 100 plus 100. That's how you get 30,100. And the output layer is going to have 100 signals going into each of these 10 neurons, which is 1,000, and then a bias for each of these 10 neurons, which is 10 more. So that's how you get these numbers. And so the total number of parameters is over 200,000 here. All right, so you compile the model, and you decide what you're going to use for loss. We're going to use cross entropy, like we said. We're going to use stochastic gradient descent, the typical optimizer. And we're going to use metrics is how we're going to measure accuracy at the end. We're going to use accuracy as the measure. So now when you run it, it will show you categorical accuracy 76. When it's done, you have each epoch go by. Here's 31 of 30. So you start with 1719 is the number of mini batches. It does things 32 at a time. So it breaks this database, which was 5,000, into a large number of mini batches. And the accuracy on training and validation sets are shown. So here's the training accuracy, 76%, the validation accuracy, 83%. But this is, of course, the first epoch. It's just starting with random values. And by the end, it's going to get up to 92% on the training data and only 89% on the validation data, which is what you expect. It should have some degree of overtraining. At some point, you'll be fitting the details of the training data more than is justified by the actual trend, so your validation data will fall behind. All right, and so here's the learning curves showing you as epoch, showing loss, and sparse, and accuracy, and here's validation loss and validation accuracy. So as you see, it starts off somewhere, and then with training, it gets more and more accurate and less and less, more and more accurate and less loss. And in general, the loss is lower for the training data than for the validation data, and the accuracy is higher for the training data than the validation data. So this all makes sense. All right, so if you want to improve performance, you can tune the hyperparameters. There's a learning rate, which is the size of the step. You can adjust that. Then you can change the number of layers, neurons per layer, and activation functions. There's a lot of things you can do here to have different models. And so here's another thing you can have. You can have a wide and deep network, where not only do you have the thing we've had here with some deep number of layers, hidden layers, but you also allow simple rules, where you allow the normalized input to go directly to the output. So you allow a second bypass. So this is not as simple as just a sequential network anymore. All right, this way it can learn both deep patterns and simple patterns, where you don't do any calculation, you just have some property. If some part of this has a certain value, then put it there. So here you do not use, you create the layers. Normalization, standards devices, the input. Here's the hidden layers that are dense, as usual. You concatenate layers. This will combine all the inputs, and then you have an output layer. But when you make the model, you put them in order. So you, here's your model, inputs and outputs, and your input is here. Concat combines the normalized and the hidden. So here's where you have done the bypass. You now combine at this layer both the hidden data that came from hidden layer 2, that's the stuff that passed through all the layers, and you also take this normalized stuff from here and put it in there directly. So you have some data that bypassed the hidden layers and some data that went through the hidden layers. That's what makes it a wide model, along with a deep model. And here you can also have where some inputs go through the wide and some go through the deep. You can set that up also, where certain features go one way and certain features go the other way. And this is what you do if there are certain features that you think directly contribute to success without having to be processed, and other features that have to be figured out. I could imagine you could have like a Tesla could have a photograph of the scene, an image of the scene you're trying to decide where to drive. And it could have all kinds of pixels that you have to assemble into, like, other cars and bicycles and stuff. And then it could have some way to recognize a red light. And it could say, if you have a red light, then you don't need to do any calculation, just stop. That sort of thing. You might have some signals that are meaningful without much processing. All right. So you might have multiple outputs, auxiliary outputs. If you have more than one thing to discover, you want to, for example, locate a picture, locate the center of an object, and classify that object into, is it a human or a bicycle or what it is. So that's both regression and classification. Now you could train two completely separate models to do it. And my Twitch has died. I hope you people have better luck with Twitch than I am. I think it may be that Brave is not a good browser to view Twitch on. Anyway, you could make two completely separate models, but it might be better to have just one combined model so that you can have some combined features that are determined and used. And we're going to talk a lot more about that later when we talk about transfer learning. You can have layers that learn something that is generally useful. And this is, by the way, how your human visual system is expected to work. The lower layers of the human visual neural pack are regarded as doing things like finding objects and finding edges, things that are useful for many different purposes at a higher layer. All right. Anyway, I'd like to go to the next slide, but I can't figure out where I am. I'm up here. Okay. All right. So you can also do it for, if you want to do regularization, you could take the auxiliary output to ensure that it learns something useful on its own. No, I can't remember the logic of this. It made sense to me when I wrote it, but I can't remember. Somehow you'd use the output to determine whether you're going off track. Yeah, I wonder if the video freeze. It froze here. I had to refresh my browser a couple times. Twitch seems kind of buggy. All right. Anyway, each output needs its own loss function, and you need labels if you're going to do supervised learning on it. Let me send a message here. Let's see if you people can hear me. Is it working now? Maybe not. I got a green box here. It works okay, good, thanks. I got a green box here showing that I have enough bandwidth, but the Twitch has been strangely buggy, at least from my end, all morning. All right, so you can make models without a fixed structure. You can do complicated things like for loops and if statements. You can combine your layers in strange ways. See, again, this is the third time my video has died in Twitch and I had to reload the browser. All right. Okay, you guys seem to be doing all right, though. That's what matters. All right. There's also something called TensorBoard, which gives you some kind of graphic environment where you can adjust parameters and try different and observe learning curves and so on. So that may help to plan your models. All right. And so to fine-tune your here's your hyperparameters. You have number of layers, number of neurons, activation functions. You have some way to choose the initial values of the weights. You have an optimizer like gradient descent, but there are others. And you can adjust the learning rate and the batch size. All these are hyperparameters, which can be adjusted to make a better model. So you can use grid search and randomized search options for them, where it will try different of those values and choose the best. And you can also integrate it with TensorBoard. All right. So you can use a graphic input. When I set the quality to maximal, I have the least of the problems. There's a quality adjustment. Let me see if I can find that. Here's settings, quality. Oh, auto. I think you're right. I'm going to set it to source. I think what I might be seeing when it blurs out is it trying to adjust the quality. There is a gear in Twitch. And I think you're right. I think what I'm seeing, it keeps going bad on me, is when it decides it's time to change the setting. Good. All right. So if you have one hidden layer, in principle, you could model anything. The only reason you use multiple layers is that turns out to be more efficient. You can get the job done with fewer neurons. And the idea here, like I was saying, in the human brain is you have one layer that finds low-level components like edges, and the higher levels look at larger scale features. And the highest level looks at meaningful shapes like faces. And in real tests of real human brains, people have found there are neurons that just pick up things like motion or edges, and there are other neurons that respond to like a celebrity's face, recognizing that one celebrity. So to some extent, your brain does in fact work this way. And that's how we get to transfer learning. So this is what's going on. You could have a model that was trained for one visual task, and you could just take the low levels of that model and reuse them for another model without having to retrain them. So you can reuse part of a pre-trained network that performs a similar task, believing that the low levels have done things like recognize fundamental components, and now I can just retrain the higher levels only. So the number of neurons per layer, input and output are set by the problem. The MNIST, for example, has 28 by 28 inputs and 10 outputs, so those are set. The old way was to put them in a pyramid shape, more neurons at the lower level and then less and less, which would seem to make sense that you need a lot of neurons to find every edge in the image by comparing every pixel to neighboring pixels, but at a high level you just need like a smaller number of objects at a higher level of abstraction. But they say in practice it seems to work better to just use the same number of neurons in each layer, which probably means that that simple idea of what the neural layers are doing is not really true. And so another thing to do is just change the number of layers and neurons until you get overfitting. Another thing is the stretch pants technique. I think Google named it this way. Start with more layers and neurons than you need and use early stopping to prevent overfitting. This prevents having bottleneck layers. If you start with low numbers of layers, you might have a layer which is not complex enough to contain the data you need, and so no layer after that can actually get any good training, because this layer, like, if you tried to drive a car and you had a really low resolution, like 10 by 10, you wouldn't have enough information in the pixels to discern the edge of the road or cars and stuff, so no amount of training the higher layers would do any good if your low layer had thrown away so much data. So this is the other way. You give more layers and neurons than you need and use other regularization techniques. The learning rate is the most important one. We've talked about this before. If your step size is really big, you'll bounce around without ever finding the bottom. If it's too small, you'll be crawling along and take many cycles of training to get to the bottom. So they say the best is about half of the maximal learning rate. So one way is train the model for a few iterations at a very low learning rate, then gradually increase it and find the value where loss starts to rise and then go back down. This is basically a grid search kind of way. So there's other parameters. We'll talk about the optimizer. We got a lot next week. We got a lot of those to talk about. And batch sizes, people argue a lot. Some people say you should never use more than 32 instances to train. Other people say you should fill up your whole GPU RAM. There's no consensus reached in the machine learning community about this yet. For the activation function, ReLU works pretty well, the one that's flat in a straight line. And for number of iterations, I say it's usually better, rather than limiting the number of iterations to a fixed value, is just use early stopping. Just iterate until it starts to get worse and then quit. That means you've hit the bottom. That's what's recommended. All right, so let's try another Kahoot. Yikes. That's what I wanted. All right. Yes, I think Anti-Ignore, I think you're right. When I set the quality to maximum, my Twitch got a lot better. It was their automatic quality adjustment that was fouling it up. All right. All right. So which one will turn a 2D image into a 1D list? Yep, that's Flatten. A good name. Describes what it does well. All right, what models have one set of layers connected sequentially? Dynamic should have been something separate. I'll fix this later. All right. All right, the deep neural network has that property. All right, that's what they call it. Deep just means multiple hidden layers. Twitch set at around 12 megabytes upload for, yeah, well, I don't know. Anyway, all right, so, all right, so which method allows a new model to use early layers that were trained on a different task? That's transfer learning. All right, good. So, all right. All right. Got those. So I'll stop this recording.